All right, hello everybody. Last 4 days of class and so much to get done, whatever. First of all, let me apologize for the mistake in what I told you. The exam 3 is scheduled for Wednesday through Friday. The times that it's listed are open correspond to the times the testing center is open, and I can't change that. I'm sorry for the confusion, and if anything I've done in terms of the schedule is particularly onerous, or however you say that word to you guys, let me know, and we can talk options. Okay, the exam covers chapters 7, 8, 9, and 10, and that's it. I have some handouts that summarize reactions in chapters 9 and 10 that I am posting, and I will also have similar handouts for chapters 11 and 12. I think 12. Yes, 12 we won't need one. 11 we will. I'm sorry, the chapter numbers changed when we went to this new edition of the text, so a little confused. All right, the other thing is we've got a lot to do, and as an instructor, I'm not that interested in cramming the class full of unnecessary material. Nevertheless, your 352 instructors are going to expect us to have talked about a lot of this. So I'm going to try to boil it down to just the essentials. All right, we talked about reduction last time, and we're going to talk about oxidation today. And there's a series of new reactions and new reagents. You're going to have to memorize some of these reagents, and then you're going to have to use your understanding of reactivity and stereochemistry to help you with predicting products. So all of these oxidation reactions involve increasing the number of carbon heteroatom bonds or decreasing the number of carbon hydrogen bonds, or both. All right, so you've already seen an oxidation reaction in chapter 10. This was bromination of alkenes, and you can tell now it's an oxidation reaction because we have increased the number of carbon heteroatom bonds. Okay. Similarly, we used the bromination reaction in the presence of water to generate this halohydrin. And that's a chapter 10 reaction. One of the things I didn't tell you can do with the halohydrin is an intramolecular Sn2 reaction. That is, you could have sodium hydride as a base, remove the proton on the alcohol to generate the following intermediate, which can then snap closed as the oxygen attacks the sigma star, the carbon-bromine antibond, to give you an epoxide. So we have this two-step reaction sequence, halohydrin formation, and then deprotonation followed by this intramolecular Sn2 reaction to give you an epoxide. Now, in chapter 11, however, there is a more direct way to make an epoxide, which I'll show you now, and it involves a reagent called metachloroperoxy benzoic acid. You don't need to memorize that structure. Its acronym is MCPBA. You can represent it as just an acid like this, but with the OH group already bonded to an oxygen. That's where the peroxy comes from, because there's an oxygen-oxygen bond. And typically, these oxidation reagents involve heteroatom bonds. So for bromine, it was a Br bond that we used. For MCPBA, it's a bond between two oxygens. And this gives you the epoxide directly. Now, you're welcome to just memorize that and move on with your life. I'm going to show you the mechanism because there's some stereochemical issues that follow. I'm not going to ask you to reproduce this mechanism. It's kind of cute, but we don't have time for cuteness anymore, unfortunately. So I'll show it to you briefly, but I'm not going to ask you to worry about it. Effectively, this mechanism involves, let's see, sorry. The pi electrons on the alkene attacking the weak oxygen-oxygen sigma star. Okay, but we're going to do something very similar to what we did in bromination. Those pi electrons attack the sigma star at the same time as lone pairs on that oxygen attack the other carbon. So we form both bonds to oxygen in the same concerted step. That will have stereochemical consequences in just a second. The other arrows are related to breaking the oxygen-oxygen sigma bond and then removing the proton from the oxygen. So a lot going on there. Some people call it a butterfly mechanism, and I think you have to turn your head to the side and be somewhat tired in order to see that. The reaction, though, is concerted. You form these two bonds at the same time. And what that means is the stereochemistry of your alkene determines the stereochemistry of your product. So if this is your alkene and you use MCPBA, your epoxide stereochemistry should preserve the trans relationship between those substituents from the alkene. And if your product is chiral, as this one is, you have to have made both enantiomers, and you get both of those enantiomers from the fact that the alkene can use either its top face or its bottom face to attack the epoxide reagent. Okay? Similarly, if you started with the cis alkene, you would expect your epoxide product to look like this, and that is a meso compound. All right? So, simple one-step reaction for making epoxides. Any questions you want to ask? I'll just refer you back to the previous lecture. We now know how to make trans versus cis alkenes using reduction reactions. So, a synthesis question on an exam might ask you to start with this alkyne, and end up with this epoxide, and you would have to know how. And so this would involve presumably you recognizing, okay, I need the cis alkene, and then remembering what you do to the alkyne to get the cis alkene. If you want to go try that as a practice problem, that's fine. I'll put the answer in the notes a little bit later. Okay? Yes?
So you the comment you said about like carbon heteroatom bonds and how that's a trend.
Sure. Oxidation is an increase in carbon heteroatom bonds or a decrease in carbon hydrogen bonds, or both. Yeah. Okay. Yes?
Would there ever be a case where they both increase or both decrease?
Can you increase both at the same time? I don't think so. At least not in the reactions we'll be dealing with. Yeah, go ahead. Okay. So go ahead, sorry.
Oh, sorry, so for the trans one, like this one, it doesn't really matter because like they're the same group coming off. Like, would you get both enantiomers?
Yeah, for the trans one, you do get both of these enantiomers. Yeah, so these two are chiral and they're mirror images of each other. And that's because the alkene can attack from its top face or its bottom face. One interesting aside that your text points out at this stage is that there's another thing you can do with epoxides, and this is something you've already done, so it's not necessarily new. This is a Chapter 9 reaction, but if you were to open up the epoxide with, sorry, we need to move the little square, don't we? No? Fine. If you were to open up the epoxide with OH minus, the product you would get appears to have the OHs on opposite faces of the original alkene. So they call this two-reaction series Anti-Dihydroxylation. Not its own thing to memorize. If you know how to make an epoxide and you know how to open epoxides with OH minus, that should be fine. An interesting thing, though, is just to note that if you open up this chiral epoxide with the OH group, you're going to get the mesodiol, which is kind of interesting. And so it would be possible to write a synthesis question where I have you end up here, and I want you to start at the alkyne, and you have to make your way all the way here, keeping track of the stereochemistry. And the danger is that you're going to look at that and say, okay, I want to open up an epoxide, but the epoxide needs to have the methyl groups cis to each other. Do you see how I've drawn this in a way that conceals the fact that epoxide opening is anti? So you would have to first say, okay, I'm going to redraw this molecule such that the OHs are on opposite sides. I'm going to pay attention to the alkene. That's going to tell me what the stereochemistry of my epoxide must be, which will tell me what the alkene must have been, and so on. Yeah? Anti-dihydroxylation just refers, you remember syn and anti before with the alkene addition reactions? This two reaction series, making an epoxide and opening it, gives you the product you would get conceptually if you added two OH groups on opposite sides of an alkene. Yeah. All right. So that's hard. That's an easy issue to get confused on, so that's worth practicing. Similarly, you should see that if we open up this meso epoxide with a hydroxide and water, we're going to get these two diols, which are enantiomers of each other. And you can go back and convince yourself that if you open up these epoxides from behind, you will get this product stereochemistry. All right. So your text has a separate section on anti-dihydroxylation. I don't think I make you read that because it's not its own thing. It's just putting two reactions together that you know now. But I think the reason your text points this out is because it's going to introduce a new reaction where you can add the OH groups to the same side of the alkene. Any other questions on epoxide making? We'll call this epoxidation. Okay, so the next set of reactions is going to be called Syn Dihydroxylation. And we're going to use reagents that have metal oxygen bonds that are relatively weak. We're not going to learn the mechanism of this reaction. So this is a reagent you're going to need to memorize. So I will start with the trans alkene. And the reagent is Osmium Tetroxide. All right, this is osmium in its +8 oxidation state. And then you use, in the second step, a strange reagent that I really don't care if you memorize. It's not clear to me what it does, but this is required to get to the final step. So I won't show you the mechanism, though I do want you to understand the stereochemical issues in the product here. This reaction takes the alkene and it adds the two oxygens to the same face of the alkene. So we're drawing here the alkene laying on its side in this plane. And then the osmium reagent is going to approach one face of the alkene. And I'm going to push arrows here, though you don't need to, and it doesn't necessarily, I'm not going to ask you to do that. The reason I'm doing it is simply to so that you have an idea of why it's a syn addition. Okay, so the alkene's in the plane, osmium comes down from above, pi bond attacks an oxygen, electrons move onto osmium, and then we make another oxygen bond, carbon bond. And that happens all in the same concerted step. So just like epoxidation, those two bonds form at the same time, and so both of them form on the same face of the alkene. So your product after this step looks like this. Do you see how the methyl groups, which were trans to each other in the plane of the page, as we make those new oxygen bonds, those carbons rehybridize and they both tilt downward, but one is still coming out towards you and one is still going into the back. Okay, and we would get this molecule plus its enantiomer. I'm going to use the plus minus symbol for that. This intermediate, your text calls the Osmolate Ester. That's not important, but you do need to hydrolyze that ester by adding water and this sodium bisulfite reagent. Again, not clear what this reagent is for. I don't care that you memorize it. There's not going to be an exam question in which everything would be right except I threw in something different there. Not interested in that. You'll need to recognize it if you're choosing among reagents and you see it paired with osmium tetroxide. You'll need to not be distracted by it. Okay, so you see, it's very important that you see that these OH groups were added to the same side of the original alkene. Okay, any questions about that? Yeah.
So is it ending with the R groups being cis?
Well, does it end with the R groups being cis or trans? Well, we won't use those terms anymore because it's going to depend on how we draw the molecule, right? These are single bonds, so I can rotate around, those bonds. But one interesting thing to notice is if you compare our anti-dihydroxylation reaction sequence versus Syn Dihydroxylation reaction sequence, notice we can start with the same starting material, the trans alkene, and if we do Syn Dihydroxylation, we get the chiral diol. But if we do anti-dihydroxylation with the same starting material, we get the mesodiol. Okay, and you should go through after class and convince yourself, that if you start out with the cis alkene and you do Syn dihydroxylation, you should convince yourself that you get the mesodiol as the product. Okay, so these are all examples of stereospecific reactions where the stereochemistry of the alkene determines the stereochemistry of the products. And notice that we have two different ways of making exactly the same thing. You can make the mesodiol from the transalkene. You can make the mesodiol from the cisalkene, depending on which strategy you choose. All right, questions there? Well, yes?
On the anti-dihydroxylation, could you go over again why it makes the meso compound again after the second reaction?
When we open the epoxide from the back side, that will lead to this product. I'm not showing you the proton transfer step where we protonate the negatively charged oxygen. So I'm just abbreviating that. This is an Sn2 type reaction, so oxygen comes in from behind the carbon-oxygen bond. That's why these two oxygens are anti to each other. And if you rotate around this carbon-carbon bond, you end up getting that.
Can you explain to me again how you got that OH just straight and not like jetting backwards?
Well, let's see. So the three-membered ring is in the plane of the page. This methyl group is coming out at you. This methyl group is going away from you. There is a proton here and a proton there. All right. So approaching, I suppose, if I wanted to show approaching of this OH group from behind, maybe this would have been the better way. In so doing, we break this bond, and then these two groups, methyl and hydrogen, as you would expect in an Sn2 reaction, they used to be angled down towards the bottom of the page, but we're going to invert that stereocenter, and so now they're angled up towards the top of the page. If that's a bit challenging to see, you can also draw it like this. Oops. And that will actually give you the same answer. All right. Sorry, we got a little bit messy there. We're going to shrink that down. Okay, anything else? Yes?
Okay, so you drew the reaction, or you labeled the reaction anti-dihydroxylation. Is it different from the one on the page before?
No. I was showing you, we introduced a new reaction called Syn Dihydroxylation, and I was contrasting this new one with the one we did on the page before.
And then there's a different Syn dihydroxylation.
Okay, hold on.
Those are different? Are there two?
Hold on. So Syn dihydroxylation means whatever alkene you're starting with, whether it's the trans or the cis, you add the OH groups to the same side of the alkene. And what I was contrasting is the stereochemistry that results when you start with the same alkene and you do Syn dihydroxylation versus anti-dihydroxylation. You get different products.
Different products, not those products the exact same.
Well, it depends on which ones you're talking about. These two products are diastereomers. Same starting material, but you get diastereomers as products.
Okay, so if I'm wrong, stop me. Syn Dihydroxylation uses the OS04 and results in the same, and keeps the same stereometrics.
Keeps the OHs on the same side of the same face of the alkene. Yep.
And then reverses the stereo.
Anti-dihydroxylation adds an OH group to one side of the alkene and then another to the opposite side. Yeah. That's difficult, and there's sort of a lot going on there. Notice that when we add the OHs to the same face of the alkene, if we keep those OHs lined up, we should also see the groups that were on the alkene in their same orientation. Right? When I line up these OH groups together, the methyl group's coming forward and then the other is going back. And that reflects the fact that the original alkene was trans. Similarly, if I add osmium tetroxide, I add the OHs to the same face of the alkene and I line them up with each other, those methyl groups, which are on the same side here, are also both coming up here. All right, now understand that's a single carbon-carbon bond. You're free to rotate around that. So let me show you one way this question could occur. Suppose I tell you that you start with the cis alkene. No, actually, let's do it this way. We start with the alkyne, and we end up with the following alkene. All right? And I tell you here that you need to have used MCPBA and hydroxide in a second step to generate this product. And then I'm going to ask you what product A is, our starting material A is, and then I'm going to also ask you what the reagent is to get from the alkyne to A. All right? So one way to solve this is to first remember that MCPBA and OH minus are the reagents we use for anti-dihydroxylation. And if I remember that, then I should be aware of the way this is drawn, right? Because the way this is drawn, the OHs are lined up with each other. And so if I don't take care of this, I'm going to make a mistake and get the wrong stereochemistry for the starting material. So what I have to do, knowing that this is anti-dihydroxylation, I have to rotate around carbon-carbon bond. And this is where a model would be useful if doing this on paper is difficult. Okay? So this tells me that when the OHs are anti to each other, the methyl groups are both below the page, right? So now it's easier for me to think one step backwards and say, okay, this would have come from this epoxide. Conceptually, I have to think backwards. I'm going to pull this oxygen off, push this one over, and make a new bond there. The hydrogen and the methyl group, because it's are going to angle now downward. Then once I get here, it can become clear what my alkene starting material was. What should the stereochemistry be? Cis, right? Remember, in making the epoxide, both of the oxygen-carbon bonds form on the same face, same side of the alkene. So if we want the meso-epoxide, we have to start with the cis alkene. So yes, product A has to be the cis alkene. Now, how do I get the cis alkene from this alkyne? That's from last time. I'm seeing a few stares of desperation, and I'm sorry. You're going to get good at this. It is going to take time and effort. The reagent we use to add one equivalent of hydrogen on both to the same face of an alkyne to get the cis product, that's the Lindlar catalyst. All right, so that's the kind of question you can expect. If I show you where the ending point is and I tell you that you had to use MCPBA, then what was this and what was this reagent? And you can write these questions for yourself. I mean, write one where now you get the same product, but you had to use Syn Dihydroxylation and see how that works out. I'll write that here for you, and then I will put the answer in the notes, but no peeking until you've given it a try. Okay. Yes?
So the anti-dihydroxylation goes through the epoxide step, but the Syn doesn't.
Yeah, the Syn is direct, all in the same step. Yep. Good. Okay. Last set of reactions for oxidation relate to converting alcohols into ketones, aldehydes, and carboxylic acids. All right, so I'm going to introduce a new reagent. This is one you're going to have to memorize too. It's called PCC, which stands for, but I'm not going to require you to know this, pyridinium chlorochromate. And again, I'm going to show you mechanism here, though I think it's not, given the number of things we need to do, it's not important enough for you to know. Pyridinium chlorochromate is the following reagent. The inium refers to the fact that you've got a positively charged nitrogen. It's a counter ion for the chlorochromate reagent. This is a version of chromium 6, and it happens to have a good leaving group on chromium. And what will happen in the presence of this reagent, the alcohol oxygen will attack chromium. Oops, I did exactly the wrong colors. The alcohol oxygen will attack chromium and chloro leaves. So this is kind of like what we saw in chapter 9 with the SOCl2 reaction. This gives you the following intermediate. And at this stage, though it doesn't happen all in the same step, you have a base remove this proton. And we don't really care what that base is because the proton's pretty acidic. It might be another molecule, it might be Cl-, doesn't matter. And then in the next step, we pick up a proton here. Again, this is not important for you to memorize, but I do want you to see the key oxidation step. And this will be helpful in you realizing that this is indeed an oxidation reaction. So all of this over here, including the lone pair electrons, happens to be a good leaving group. And that might be difficult for you to notice or understand, and that's okay. I would have to maybe give you pKa information if you were to predict that that's a good leaving group. But for now, just take my word for it. And notice that if we say the oxygen bonded to the leaving group is the alpha position, then the carbon bonded to the oxygen is a beta position. And now you've got a beta proton and a really good leaving group. So you can do elimination style chemistry, leaving group leaves, and that gives you this aldehyde as product, and then you've got the chromium leaving group, which we're not going to worry about anymore. All right? So that is a reagent that will take the alcohol, in this case a primary alcohol, and convert it into the aldehyde. Now there were 2 protons on that beta carbon. One gets eliminated, the other is still there, and that's where we get the aldehyde. Okay, questions about that? Yeah?
Would you get a ketone if you do it secondary?
Great. The question is, what about the secondary alcohol? Yes, exactly the same thing. Same mechanistic steps with PCC. I'm going to skip ahead to the key one, and that is we will see this intermediate, and again you've got an alpha oxygen, a beta carbon with a beta proton. Now there's only one beta proton, so when a base removes that proton, and again the base doesn't have to be particularly strong, Cl- is fine, that generates a ketone, and there's no more beta protons there. So you have the ketone as a product. Yes, secondary alcohol leads to ketone product. All right. This pyridinium chlorochromate is an organic soluble reagent, and so typically we will use organic solvent. A popular one is dichloromethane. I don't mention that because you need to know it, but because that's a key reason why we can get to the aldehyde and stop. All right? Because if you contrast the ketone with the aldehyde's still got a beta proton there. And so there's a possibility for another elimination step, though something else has to happen first, and that something else involves water. So the fact that we don't have water present here allows us to get to the aldehyde and stop. Okay? Now, there's a lot of reagents, SOCl2, POCl3, now PCC, PBr3. There's going to be a lot of things you need to keep straight, and so you're going to need to draw on whatever memorization skills you have. If that happens to be flashcards, that can be useful to you. All right. So would this work with tertiary alcohols? No beta proton, so no oxidation of tertiary alcohols, right? Now, let's introduce conditions for going from the primary alcohol all the way to the carboxylic acid. So this is, instead of PCC oxidation, what I'm going to show you, your text doesn't use this name, but a lot of organic chemists do. It's the Jones oxidation. And this will take a primary alcohol and take it all the way to the carboxylic acid. And the conditions for this reaction are CrO3 and H2SO4. There are some alternative conditions that are very similar that your text introduces. This is the only one I'm going to hold you responsible for. And the mechanism I'm not going to go through in a lot of detail. Basically, the chromium reagent looks like this. So we're going to have the oxygen attack the chromium, and that's going to lead us to exactly the same intermediate we saw before with PCC. Okay? So at least in the first round of oxidation, the mechanism is basically the same. It involves an E2 style reaction in which we remove the beta proton and the leaving group leaves, and we're left with this aldehyde. Now, at this point, the aldehyde oxygen isn't really nucleophilic enough to attack another equivalent of chromium. But in the presence of water and under acidic conditions, which we are here, we've got H2SO4, that oxygen can pick up a proton from the acid. And again, this is what you'd predict. The HOMO of the aldehyde is lone pairs on the oxygen. And that can get you in equilibrium with this protonated aldehyde, which we're going to call an oxonium ion. And then that oxonium ion has a resonance structure in which the positive charge is on oxygen. Whoops. Has a resonance structure in which the positive charge is on carbon. You see how we got there? I took this pi bond and moved it onto the oxygen as a lone pair. Again, what I'm showing you here is not going to be something I'm going to test you on, but I'm trying to illustrate why this reagent works this way. Water attacks the positive charge to give you the following intermediate, and then we can regenerate our acid by removing a proton from the OH group. And that then converts the aldehyde into something that's in equilibrium with the aldehyde. And the structure aldehyde, we needed just a E at the end of that. The structure here is called a hydrate because we have basically added water to the aldehyde. Now you've got two oxygens, so another equivalent of CrO3 can come in, and we can get, again, the intermediate in which we've got a good leaving group in terms of the chromium. And again, we can have a base, probably just the conjugate base of our acid, remove the proton to establish the new carbon-oxygen pi bond. Your leaving group leaves, and you've got the acid. But the key to forming the acid is the carboxylic acid is the presence of water. No water, no hydrate, no carboxylic acid. Because you have to have the hydrate if you want to go on to the carboxylic acid. Again, that mechanism is purely for your insight and edification. You're welcome to ignore it and just memorize that the Jones oxidation conditions lead to the carboxylic acid, whereas PCC stops at the aldehyde. Yeah?
I don't know if this is important, but what are the implications of equilibrium instead of full reaction?
What are the implications of equilibrium arrows versus just the forward reaction? Not a lot. I think there's usually, even if this were a free response exam, there's no points attributed to the nature of the arrow. This is just meant to communicate that actually when you have the aldehyde in water and in the presence of an acid, there's always going to be a certain percentage of hydrate. And so it turns out, and I don't think your text necessarily mentions this, but it is the formation of that hydrate that is critical for the second step of oxidation. You can use the Jones oxidation conditions for secondary alcohols if you want to. I've done that before. No, have I? Can't remember. In any case, it's fairly straightforward, and so and there's no problem there. And the reason that we don't have to worry about a second round of oxidation is no beta protons at that stage. We can definitely, in the presence of acid and water, form the ketone hydrate, but notice that there are no beta protons on that ketone hydrate that we could remove in an oxidation step, and so there we stay. All right. Anything else there? Yeah.
So because water needs to happen when we just write H2SO4, we're just, you can't have H2SO4 acting on acid without water, so it's just implied.
Yes. When you use H2SO4, it's aqueous, and the presence of water is implied. Oh, how about that? I found something cool in my notes that I was looking for desperately last semester, and now I found it. That's fun. We won't talk about it because it's extraneous. We could talk about fats and oils and hydrogenation of them. I'd love to talk about that, but we're going to move on. Okay, so that concludes Chapter 11. That's actually a good time to pause. So let's take 5 minutes or so, maybe 10, and then we'll be back at 5 minutes to the hour to proceed with the next chapter.